Hello, my name's Chet Sandberg. I'm the co-author of a paper entitled MI Cable Heater Design and Deployment Advances in Downhole Applications. What we're talking about here is a long heater that operates at a high temperature in a long horizontal well in Alberta that is used for either viscosity reduction or in situ upgrading process, converting 10 API oil into 40 API oil. My co-authors were Dave Burns, senior member of IEEE and working at Shell P&T, and Edward D. St. Remy, also at Shell. I'm retired from Shell, having worked on this project for a number of years. So the summary of the paper is we're going to talk a little bit about applications for downhole electrical heating. Then we're going to go on and talk about the heater design and the insulation characteristics and the manufacturing of the cable. Then we're going to talk about the pilot which was done in the Grossmont area of Alberta. And then we'll have some conclusions. So the applications for MI cable have been numerous in the past. The first ones were probably back in the mid-50s, and they've been used as either pilot tests or now becoming commercialized in a number of applications. One of the applications is flow assurance to mitigate paraffin and hydrate formation. Another application is cyclic steam replacements. The cyclic steam stimulation is where you put steam into the well. It's sometimes also called huff and puff, and then you wait for a while for it to reduce the viscosity, and then you produce the oil. This is used in the Central Valley of California a lot. The good thing about using electrical technology is it really reduces the water consumption. In fact, in some wells in the Bakersfield area, we have absolutely no water cut. We also have used it for viscosity reduction in Alberta and other places. You don't have to use steam or diluents. Then there's also a replacement or a preheating for SAGD, steam-assisted gravity drainage. Sometimes there's used up to 7 barrels of water for every barrel of oil that's produced. If you preheat the well or even use it as the major heating source, you can reduce that to less than 3 barrels or down to your 0 barrels. And the final application is a really high temperature requirement. It's a Shell patented process called in situ upgrading, and you have to raise the temperature of the formation to something like 340 degrees C, and you wait for a while, and it changes the oil from the heavy 10 API into something between 25 and 40 API. You can see on the chart in the lower left-hand corner how sensitive the viscosity is to temperature. Even reducing increasing the temperature by 100 degrees C, you can reduce the viscosity by orders of magnitude. This is a logarithmic scale, and you can see that reducing it down to, say, 10 to the 2 centipoise is enough to start producing in a very good way. On the lower right side of this slide, you can see the initial oil in the left picture, and then when you go through the in situ upgrading, you can see the clear high API oil on the right. So the electrical characteristics of the MI cable are shown here in the first slide. It's a logarithmic function for the voltage that can be applied, the peak voltage per mil. You have a inner conductor diameter of A, which isn't shown here. The B diameter is the inside of the outer sheath, and so this distance is the distance across the electrical insulator, MGO in this case. MI cable has been typically very sensitive to volts per mil in past applications, and no processed MI cable is operated at above 600 volts. In fact, IEEE 515 specifies that the megger tests have to be lower than they would be for polymer insulated cables, so you don't have some destructive characteristics that you apply to the MI cable, because it seems to be a combination of continual stressing that'll help the failure modes, and there's a number of failure modes for MI cable. one of them is high temperature, one of them is high voltage. The magnesium oxide is very NTC, negative temperature coefficient. As a consequence, as the temperature rises, the conductivity of the MgO increases, and this is many orders of magnitude from room temperature up to the 650 degrees C where we're operating the cable. So one of the things we were faced with is really improving the electrical characteristics of the MgO construction in the MI cable, and that has been done. There are two ways to make the MI cable. One is a drawn process and one is a seam welded process. The drawn process, you have a start tube of a diameter, say a 2-inch diameter. You put the center conductor in, as you see here. You put powder fill around it of MgO, and then you run this through a drawing bench, and as a consequence you reduce the 2-inch diameter down to a 1-inch diameter or something like that. And if you go from 2 to 1 inches, you get 4 times the length. But if you have a 50-foot start tube and you get 4 times the length, you're only up to 200 feet, so you have to put splices in. And that's one of the killers in this, is making a number of splices to make a very long cable. So the drawn process has a limitation in it intrinsically of what the start size is and what the final diameter is. Now the seam welded process is different, because what you do is you construct the outer sheath from a long strip roll of plate type material, and as you're constructing it, you form the outer sheath around both the center conductor and MgO blocks. As a consequence, you can make these very long, and people have made things that are 9,000 feet long with this process. And then you seam weld the top, and after you've seam welded it, you run it through the roll mill, and this compacts the MgO. You want to go from a 60% theoretical compaction up to something like an 83% theoretical compaction to give you the electrical characteristics. Low voltage cables have been operated up to 8 volts per mil, while the medium voltage cables that we're talking about in this paper have operated up to 24 volts per mil. This paper will then explore how this improvement can allow for longer heater lengths and, as a consequence, much lower energy losses in the overburden. What you basically have is an extension cord to get the power down, and then the heater cable. And here we have a review of the drawn and seam welded cables. As we said, the MgO is in there, and the criteria are logarithmic for calculating the voltage stress. The conductor size is limited by the final cable diameter, as we said, and voltage rating in drawn cables, and that isn't limited by that in seam welded cables. Here's a map with the location of the pilot here in the Grossmont, which is an area in Canada that's halfway between Fort McMurray and Peace River. It was called the North Field Test, done by Shell. It's in northern Alberta. The objectives of the demonstration were to test the mechanical integrity of the system, the heater and subsurface interactions as we heated the heater up for the first time and cycled it. The heater deployment and operation of this, this was a 610 meter heater, so it was about 2,000 feet. And we wanted high power injection rates, greater than 1,000 watts a meter, at high temperatures, 650 degrees C. Here's a picture of the well and the heated section in the horizontal. You can see it's 610 meters long, and there's a 35 meter heated expansion section at the end of the well. There's a termination. We've got a 3-phase heater in there. We've got instrumentation, and we've got about 250 meters of overburden that we have to go through. If you look at the top right cross section, you can see that the 3-phase heater is there. You have the 3 phases. At the end, they're connected together in what's called a Y connection, WYE, which is makes the integrity of the system a lot better, and also gives you some electrical characteristics which are very good. You can see that the heaters are there on a little platform, and that was put together so that it could be inserted into the 4.5-inch coil tube for deployment. And here's a picture of the deployment manufacturing process. Basically, what we're doing here is we're putting the heater into a 4.5-inch coil tube, and it's laid out on a runway of an old airfield in Texas, and then pulled in along with all the instrumentation. So when you get to the site, you're going to be deploying a 4.5-inch coil tubing and not 3 separate heating elements with all the instrumentation attached to it. So we have the MI cable, fiber optics, and the thermocouples all pulled into the coil tubing, and then when it's in this coil tubing, it's spooled onto a reel. And here we see the reel. It's laid on its side so that it can be transported under bridges and such things on the transporting up to Alberta. It was first shipped by rail to Edmonton, Canada, and then was shipped by truck to Westbaska, and then transported over a logging road and narrow bridges during winter when everything was frozen. And you can see the lower right-hand corner here is in fact going over a bridge where everybody had their fingers crossed, because it was not clear that we were going to make the width or the loading, but it went across fine. And here we have pictures of the deployment. We have the coil tube, which is now shifted to a vertical position on the coil, going up over the gooseneck, going down into the injector. The blue part here is a straightener, and then it goes into the deployment into the well. You could both push and pull the heater with the coil tube injector. And here are some of the electrical components that we used in the application. The middle slide shows the end terminations where we go from the MI cable into the medium voltage tech cable. There was a special connector that was designed for this by both 3M and Tyco Electronics, so there's sort of 2 vendors for this, and it has stress grading in it and all the things you need to go from an MI cable system into the tech cable system. That's a partial, you can see the partial assemblies in the center picture. Then a little lower on the right, you can see the shrink wrapped, cold wrapped end connections, and then further down you can see some of the cables with the surge protection equipment to protect against lightning and welding and all the other types of electrical interference that you might get. Here we have a schematic of the layout at the site. On the left we have the well and the bubbler and all the instrumentation going in there. In the middle we have the electrical distribution equipment and the generators. We have a 2.8 megawatt generator. We also have a tank farm there which has 11,000 barrels of diesel fuel, and then on the far right we have some nitrogen tanks we use to flood the well with. Here's a picture of the power supply and what we've got there. We have the 2.8 megawatt generator system with 11,000 barrels of diesel storage. In the lower left hand corner you can see some what's called VVTs, variable voltage transformers, which are powering each of the 3 legs connected in a Y formation. The heater supply then schematic is on the right. We have a 50 amp 10-second low resistance ground to look at what the ground currents are, and we have a 5 kilovolt medium voltage 5051 protective relay system installed. Here's a picture of the architecture for the control of the heater power, instrumentation, and the data acquisition. We had redundant PLCs, programmable logic controllers. We had band center control for the VVTs. There were high temperature thermocouples. A bubble tube measured the pressure at the head end of the heating element downhole. We had power injection control. We had P&ID control on the power input. And we had a fiber optic distributed temperature sensor monitor system software. This all worked very well except for the fact that the DTS through cycling failed early in the experiment in the pilot, but it still gave us information on the initial heat up. It's very hard to find DTS systems that will operate at 650 degrees C. They operate once, but then they usually fail on the cool down. So here's the data flow. Everything went into the SCADA system, supervisor control and data acquisition system. There was an HMI at the site, and then that went into the PI collector, which is the software we used, and then all the data was sent on the network back to Houston, and you could operate and monitor everything from either Houston, Calgary, or on site. This is a graph of the first few months of operation. The facility gave us an enhanced thermal cycling program at the beginning because it was difficult to keep the power generation on. It kept tripping off at the beginning until we solved a couple problems. But you can see it went up and down here a lot, and after this we did have 196 days of high heat injection with an average temperature of 650 C for 27 of those days. So this was where we went in and looked at the T-maxes and cycled back and forth, and then after this was when the 128 days of high heat injection was used. And you can see on the bottom here the temperatures along the heater are fairly even. If you have the same thermal diffusivities in the near wellbore, you're going to get fairly good temperature consistency along the horizontal well. One of the things we were interested in here was drying out the well. We had two different regimes basically, where you initially have moisture water in the near wellbore, then you drive that out, and then you have conductive heating into the formation. And we had both of those basically going on in our testing. So the pilot summary is we installed and operated the longest high power subsurface heater at the temperature range that we know of that's ever been done. We operated a 610 meter MI cable for 4 months at the high injection rate that we talked about in the previous slide. We demonstrated that the 4.5 inch coil tube could deploy the heater even at cold temperatures. We also determined what the open hole heater deployment friction factors were, which is good for figuring out how far you can really push this heater into a horizontal well. We achieved a temperature of 650 C in the subsurface. We investigated the time to reach maximum heater temperature with water boil off, and we demonstrated the robustness of the heater in thermal cycling. So the conclusions of this test were, we have indeed a process to increase the operational voltage capabilities of the MI cable. As I said before, it's usually limited to the 600 volt and under regime, and now we have tested, verified commercial heaters that can operate at, this one operated at 4160, and we think we can characterize it at 6,000 volts on a Y connection. We reduced the need for MI cable heating splices. A lot of the original pilot work that's been done was done very well with splices, but you can't use that in really long cables, both because of reliability and economic reasons. We increased power density capabilities where before people were talking maybe 100 to 300 watts a meter, and now we're operating at 1,000 watts a meter. We proved the deployment technology. We think that it can go into a coil tube. In fact, new designs now aren't in a 4.5 inch coil tube, they're in a 2 7/8 inch coil tube. These heaters were 1.2 inches in diameter, 3 of them in one coil tube, and now we're looking at 0.85 inch diameter heaters in a 2 7/8 coil tube. We have a long manufacturing capability. Many meters of this has been made on this manufacturing capability. This is sufficient instrumentation technology. As I said, the downside was that the DTS didn't operate, but we had it backed up with 24 thermocouples, which gave us the information we needed. And the DTS system will probably be too expensive for commercial applications in the long run, but for a diagnostic and a pilot, it's really could give you some good information. We improved the power control technology. We proved that the variable voltage transformers were adequate and very good, actually, from an economic standpoint in this application. We have the logistics and transportation proven by just moving the thing all the way from Texas up to Alberta and deploying it up there. The coil tube system is definitely a proven system now. And we proved that we could do a 4.5 inch coil tube deployment. So all of the objectives of the pilot were verified and produced, and we're very excited now to have this as a technology which we can go into commercial application in either viscosity reduction, cyclic steam, or SAG-D preheat. So there's a number of places we can use this, and we're excited about doing that. As I said before, this is a product that's manufactured by MCAAA in the UK, and if you would like a copy of the technical paper that this presentation came from, please send me an email at chettsandberg@IEEE.org, or get in touch with the MCAAA people, either off their website or calling them at this number. And we hope this has been useful to you, and we hope we can help you solve some of your problems in long horizontal or vertical wells with this technology capability. Thank you for listening to this.